Okay, we're streaming again, and here you are. We stopped at the materials. So one of the important characteristics of OBG is the separation of material properties from geometry. So it's kind of remotely similar to web, when we have like structure on one hand and like visual part separately, and this is like it comes in two different files. OBG that actually defines the geometry and surface and shape, and it comes also can come optionally as a material library with like this syntax mtl lib with file name and like mtl extension. We use useMTL to refer particular materials and apply it to the geometry that immediately follows it in the OBG. So it will be easier again if we have a look at the example itself. For instance, let's take the extension is MTL. Yeah, here you are. So again, like it starts with comments that shows like by whom was it created and when, and this kind of metadata kind of, and then we define different materials with new MTL expression and then any arbitrary name, for example, sphere material, short box material, left wall, but I think this is not very professional, so this actually is called by the objects this material is applied to, but usually it's way more logical if you call them like gold or glass, metal, actual material names, wood, and whatever you encode here. So how is this encoded? NS is specular exponent. Higher this number, more sharp and bright is the specular reflections. Ni is refractive index, so how much the light is bent where at the surface of two media when it transmits the light. You are familiar with refraction, right? From physics, optics, probably. Yeah, D is, I don't remember which English word it stands for, but it's actually opacity. So in this case, it's equal to 1, so this means that it's just reflecting, it doesn't transmit any light, so it's opaque. And transparency is its opposite, so it's kind of equal 1 minus D. So you can indicate either opacity or transparency, the same. The transparent filter is a filter where you can indicate how much of each RGB channel should the object transmit or block. So if it were transparent, and if we had, for example, 0, 1, and 0, it would transmit only green light and block completely red and blue. This is illumination model, so there are different models predefined in this specification, like for example ambient on and diffuse off, or like ambient, diffuse, and specular on, and so on, different combinations of lighting models. So this is just number of lighting models. We will have a look at the specification. And here comes the color information encoded. So any guess what each line represents? So it should be pretty intuitive, I guess. So what is KA, KD, KS, KE, and those, like this matrix? Yeah?
Ambient, diffuse, specular emission.
Yeah, exactly, RGB.
Yeah, RGB.
Yeah. Yeah, exactly, that's absolutely right. So this is ambient color, this is diffuse reflection color, specular one, and we have no emission for this material. And other materials are defined likewise, so exactly the same way. We can have a look maybe to the specification. Yeah. So this is MTL specification that defines, like, we have color and illumination statements. We can include some texture, reflection map, and we define it by new MTL. And here are like all the different keywords kind of defined and explained. You can have some textures included. You can have bump maps included and lots of sophisticated stuff. So this MTL specification is pretty powerful tool to indicate your material appearance for a particular model. And here are, like, if you have a look at this, you will see all different possibilities. You have like color texture, bump texture, and so on. Yeah, let's get quickly back to the presentation. Yeah, here you are. In this case, we had like most straightforward implementation of color. So ambient one like KA and RGB, but you can also refer to the spectrum. Like instead of RGB values, you can have some spectral power distribution across the visible, or maybe no. Infrared and UV doesn't make sense because they are invisible to the camera. Yeah, and you can also, except for the RGB, you can have X, Y, Z color space. So you can indicate color coordinates either in RGB or in X, Y, Z. So it's just another color space that is derived from human color matching functions. And our sensitivity to different spectrum, and the Y is selected so that it matches the luminosity function. So do you remember I showed this kind of curve, our sensitivity to brightness across the spectrum? So Y channel, if you separate it, is just a luminance channel, and it's pretty useful in some cases, and you can simply convert between RGB and XYZ using some matrix multiplication. But maybe we'll look in it later if you're interested on material appearance lecture. And yeah, what I've said, like diffuser reflection, keyword, specular reflection, and the same things, illumination models. We will have a look at this, and you can have supported heat maps, procedural textures. Does anyone remember what is procedural texture? We had it on the texture lecture. So we had either like, yeah? You want
textures that are automatically generated in a shader or on the GP?
Using
you use equations.
Yeah, mathematical expressions. So instead of loading from the file, you have some mathematical expressions like sinusoidal function that defines the color or like other aspects of texture. Yeah. And bump mapping and material textures and so on. Yeah, I forgot to show the illumination models in the specification. Should be 10 of them. Search. Oh yeah, here you are. So here are 11 illumination models, and you have like different combinations: color on and ambient off, color on and ambient on, highlights on, reflection on, and ray tracing, transparency on, and reflection also on, using ray tracing and so on. So it's kind of different models of illumination, and you just indicate the number and you use the following one here, like casting shadows onto invisible surfaces, or like lots of different combinations of them. And yeah, that's more or less it on materials. So just to make a long story short, we have material library MTL file where we define material properties by those parameters, and then we just refer to that material in OBJ file using use MTL, and then it applies these properties to all faces and vertices below it or within a given group. Yeah, loaders. So I showed you like a very simplistic loader. Actually, this is a pseudocode, and it's kind of C++ implementation, but you don't need to worry too much on it because there are some loaders already available for you. So actually I will review two options. Tiny object OBJ loader, as the name implies, is only for OBJ files. It's very compact, very fast, simple, but also limited in functionality. For example, it supports only C++, but it has like flexible integration with OpenGL, Vulkan, and CUDA. And there is async, that is asset import library. That is very powerful because it supports many different formats. So formats are also other than, in addition to OBJ, and it has bindings with many different languages, including Python, I think, if I'm not mistaken. So you have like option, if you work with C++ and only with OBJ, you can go for tiny object loaders that is very simple and fast. Or if you have some sophisticated task, you'd better work with ASIMP. And I think that's the one we're gonna work on tomorrow on the lab, the ASIMP, Asset Import Library. Yeah, let's move to other formats. The first one after OBJ is like 3ds, that is an industry standard. And we can say that it's kind of opposite to OBJ in many ways. First of all, it's binary. It's not that well readable. Like in OBJ, we had vertices. We could identify what line corresponds to what, like whether it's vertex, whether it's face, etc. Well, this is binary and very difficult to read and interpret. It's proprietary and also has some compatibility problems. And yeah, it's based in OBJ. We had flexibility of moving the lines without disregard of the sequence. The only case where the sequence matters in OBJ is when you group the objects or like create a group of different elements, because everything that is below that grouping statement or smoothing statement is included and covered. That's why. Otherwise, you have flexibility to move the statements around. While here we have strong hierarchy, it only allows modeling triangles, while in OBJ we can have any number of sides within a polygon. At least like very high number. I'm not sure whether there is a particular limit, but you can have like 4, 5, 6, or very complex surfaces or curves defined. It supports 25,000 vertices per single mesh, and per single mesh we can apply single appearance or like material properties. Well, no directional light supported. Actually, we have no light support at all in OBJ, so it's also kind of it's not very different from that. So we don't support. There is no light support in OBJ, but the good thing is that it includes lots of scene-related data, and it's very suitable and actually suited for this 3ds Max software, and that's why it's kind of limited to this particular application. So this is how its hierarchy looks. We have kind of root as a main chunk, and then we have like version, editor, an object block that includes like vertices, faces description, material for the faces, smoothing, mapping. So everything is very strictly prescribed. The hierarchy is strictly prescribed here. Like then we have camera, material names, bump map. So it's a very clear order with a very clear hierarchy. And as you can see, it's not very readable and understandable. So it's easy to write the loader for OBJ because you know what's there and what each line does and means, while here it's super complicated to write your own loader to deal with all this not very human readable stuff. And then we have, let me see, just a second. Okay. Yeah, that's it. Here, and we have the next format that is a web standard, X3D, that was defined by Web3D Consortium. And it's completely XML based and therefore very easy to interpret and understand. And it's ISO ratified, and it's actually a very established standard for web and therefore widely supported. So you can, in most cases, it's supported in your browsers. So you can support use this model in your browser and on the web. And we will see the example. So it's successor of this virtual reality modeling language format, and kind of replaced that for web applications. But it's not only a module that has information about the shape and the appearance. It includes lots of sophisticated stuff like navigation, interaction with the model. You can give input to the model. We will see this like dynamic loading, and it's better to have a look at the example, I think. But yeah, before that, yeah, X3D comes in different profiles because it's very powerful and very sophisticated. Sometimes it's not really necessary to have everything inside. So in order to compress, there are different profiles with different extent of covering different features. Like we have this interchange, the very basic one that supports like standard stuff like model, texture, basic lighting, maybe a little bit of animations. Then we have another profile, interactive, that, as the name implies, enables interactivity between the user and the model. Like it can have, like it can be related to some sensors. For example, have elevation grids. And then comes immersive, that is even more powerful. We can use scripting here and script anything, like for example using JavaScript and do some operations for some particular actions. We can include audios, fog features. I think fog here means the technique when the distance between the pixel and the camera is considered, and the farther away ones are kind of visualized as foggy or blurry, considering the human vision, because something that goes far is not very sharp and clear anymore. So I think this is what it refers to. And then we have the full support, full package with super powerful capabilities. Like you can have geospatial information, so you can use it for GIS, You have human interaction and animation. You have nerves that are like splines. Instead of defining the surface using primitive triangles that is still kind of rough, there are like in splines, there are control points that are used to calculate the surface that is very smooth, that is kind of foldable, and it gives like smoother and more refined surface. I think it's, yeah, let's have a look at the examples. That's the best way to learn, I guess, again. So we have lots of, which ones? Yeah, look how complex stuff can be implemented here. So this is the terrain of the Puget Sound. This is near Seattle, I think. So you have the whole landscape of the very large area modeled. So we have this landscape here. I'll turn this off not to eat all my RAM. And what else is interesting here?
Can you load like a map in async, or?
Sorry?
Can you like load like the map in async, like those file types?
I am not 100% sure, but I think yes, it should have support because ASIMP has very broad range of supported formats. I don't remember particularly E3D, but I guess intuitively that it should. Do you remember whether ASIMP has E3D support? I'll have a look later. Yeah. So. And for example, this teapot is an interesting one. So you can have a look from different angles. And you have these three handles of 3 axes, and you can kind of interact with the teapot. You can move it like this. Yeah, let's have a look at the code itself, like the source. I should have this downloaded, I think. Yeah, it's this one. Oh yeah, it's this one. Source, yeah. Oh yeah, here you are. So here it is. Yeah, so as you see, it's standard XML, like very similar to what you have probably seen in XML, and then we have some styles defined. And here we have scripts for particular events, like for example, what happens when we have translation. There we have like, I think there should be a rotation event. Yeah, we have a function for a rotation event, and there are like particular things happening. So we have actually scripted what we want to happen when particular event takes place. And here starts the actual body. And this is the specification that we are using E3D format. And as you see here, you have like, you can indicate the viewpoint, the camera orientation, and then there are like actual shapes defined. So this is a teapot itself. So this should be, yeah, this should be the indices that define the facets. And here are the coordinates. And then we have other shapes like ground plane, and then again material defined, and again another object defined. I think this is a handle, yeah, rotation handle. Yeah, that's how it looks. So I think it's also very readable as the OBJ, and in contrast with OBJ where you have just those vertices and faces indicated, you have scripting possibility here, so you have way more control and lots of interaction available. Let me show some other examples. So, oh yeah, I think this is an animated example. And you can also interact. For example, I can hold this ball and move a bit, yeah. So I think the source should be here. Yeah, it's the right one. So the content of this one is also interesting. Let's see the source. Yeah, so as you see here, you have just like a simple circle, but what's interesting here, we have the timing parameters, cycle intervals, the loop that makes this circle move, and we have some like positions interpolated when it moves, and the route defined how it should move, and so on. So again, support for interactivity. So I haven't worked on this on like practical matters, but if you have a look at this, I think if you need, this can be a very interesting thing to look deeper and get a very comprehensive understanding, because it's very powerful. All right, those are the examples, and we're getting close to the summary. Yeah, well, let's briefly summarize the 3D model formats. STO is the simplest one that just names the vertices in the mesh. It doesn't support many other stuff. So here, like, if you compare that with X3D that I just showed you, it has support for approximate mesh, is the one that is defined using like triangles or that kind of primitives. Precise mesh is that smooth spline-based mesh. CSG is the method. What does it stand for? Just let me have a look. Constructive solid geometry. So what it implies is that you have lots of simple shapes like spheres, cubes, triangles, pyramids, and then you compose a more complicated shape with the Boolean operation of addition and subtraction of those primitives. This is a CSG. Their appearance attributes supported like color, material, texture, and the scene attributes, camera, lights, relative positioning of the camera, and animation. So you can have a brief overview which format supports what. OBJ is reasonably good. It has both approximate and spline mesh. It supports color, material, and texture, but no lighting or camera information and no animation. So for powerful stuff, we have this X3D. And yeah, just to have a look to make sure that you understand the differences between different meshes. So yeah, this is the approximate mesh where we approximate the surface using these primitives and covering the space by triangles, for example. And then we have this smoother one, the spline-based one. So we have these control points, and then the surface is mathematically interpolated between those one, and it's like very smooth. And then the third one, so we have the primitives like sphere, like simple objects like sphere and this cylinder, and they are just composed and used to construct more complicated objects. So this is a general idea. And yeah, and finally, the final slide for today. WebGL. WebGL is actually, I think, pretty much the same as OpenGL, very similar, but used for web applications. So you can mostly use your native OpenGL code. Just if I'm mistaken, just correct me, for like implementing on the web. And it comes also with very interesting stuff like, first of all, you can test support of your browser, so it's executed in your browser. Get.webgl.org, and you can test whether your browser supports WebGL. So if this cube rotates, this means that you have WebGL support, and you can have a look on WebGL generated content. Another interesting thing is WebGL samples. So it's also like very broad spectrum of stuff. Like for example, this is implemented in WebGL and just running in your browser. So all the rendering is implemented in WebGL, and here, so lots of cool stuff that is possible with OpenGL is also possible with the WebGL. And yeah, here we have some information about the content. So you can just have a look on those. And the last and very cool thing is Shader Toy. That is kind of catalog of WebGL shaders. So we can have a look, for example, so shadertoy.com. Let's have a look on this. So here it's running live. We have this kind of animation. You can have a look what are the shader inputs. We are using some uniforms. And here is the actual shader code. And you can play with this, and you can, like if you're interested in WebGL, this is a good thing to start looking into. Maybe Halvor is more competent on that, so would you add something on this?
Yeah, so I'd say it's more about the changing the, or playing around with the fragment shader, because if you press the new button up in the corner, you're given a simple fragment shader.
Okay, and you're coding yourself.
Yeah. So.
And you see the results in live.
Yeah. You can compile it just down there.
Yeah, from here.
You have help with the different sort of functions that are available in GLSL for open.
So which one is it? Help.
Yeah, that one. For WebGL. And it's all, yeah, I don't know, you've used it more, I think. Any more to add?
All the geometries are rendered in just the shader. It's not like a mesh or something going into it. It's like the shader uses maths to make things.
Yeah, so if you want to sort of work with geometry, it's not really the same kind of shaders you're working with anymore. You're not given the vertices through a vertex shader. You're just sort of supplying mathematical formulas for the different shapes, if that's.
By the way, is it possible to load the models directly to the?
I think you can supply them through the different channels, but I haven't really played around with that.
You can put textures in channels.
Yeah.
But you can't load models. It's always a full screen shader. So
Okay.
you can't load models or anything.
Okay. Yeah, and there are lots of cool stuff. I remember there was Pac-Man.
Yeah.
This one, there was a cooler one.
Be aware though that this website can crash your computer if your graphics card is not up to date.
So kinda inspiration, whoever wants to implement 3D Pac-Man. Well, that's more or less it for today. Again, if any of you was late, I want to ask you to show up tomorrow because Halvor will present last year's assignment 2 results so that you can get the idea what is the kind of extent of the work and the scale and maybe some interesting concepts as well, like the idea itself. And whoever hasn't presented yet, please show up tomorrow and present, maybe there on the stream. Well, yeah, that's more or less it. And if you have any questions, OBG, are all those formats, model loaders, clear more or less the ideas? Why do we need models at all? And how do we handle appearance?
But if you want to render a huge map, you just make like, you don't put that in just one OBJ file? Or
Huge, you can theoretically, you can, like there was a large scene, which one was, I'll show you again. Well, it depends on the extent. If the file becomes too large, it might be too cumbersome to handle and load. But in any case, I think it was this one. Casual effects. Yeah, we have like pretty complicated scene which is also like very large scale. We have the building, the street. So you can do that, but as you see, we have like 12 million vertices. So there is always a trade-off between like three things actually: compatibility, features, and memory and speed. So it might be very convenient to have everything in one place, but in terms of speed and memory, it can be very not very smart decision to do. But you'll see that from practice. But what you should, I think, definitely do for these complex scenes is to group them. So to, for example, I mean, nose. Yeah, so I mean this kind of grouping. You group the primitives that represent the, for example, one object or something is made of the same material or something is easier to handle separately. Because if you don't do that, then you have 12 million vertices, and how do you know where should you apply each appearance attribute? So in that case, if we go back here, in this case, yeah, you can have lots of groups and lots of different objects. Like you can have, for example, windows. You can have like different parts of the walls as a single group or single object even. So this kind of arrangement is very smart, but whether whole scene should be fitted within a single OBJ, yeah, I don't know, that comes from maybe experience and practice. You will see how efficiently it runs on your machine and then decide. But generally OBJ is not very large, as you see, like even though this is 12 minimum vertices, it's just 48 MB. But if you have something very full scale, like whole town, that might be too much. So yeah, again, application dependent.
Kind of depends on your C++ application. If you're loading this into your graphics project, you might struggle with culling, for example. So cutting away the pieces of the map that isn't supposed to be rendered is more difficult if you load the entire thing into one sort of
because it's
abstraction.
too complicated and too much
Yeah,
overlaps.
but that all depends on how you load it into your programs context, I guess.
Okay, if there is not any other question, then see you on tomorrow's lab, and we will play with async loader. Yeah, great.